All right, so if Anna wants to win this race, that means she needs to have enough distance to make up the 50-meter head start and catch Ray, who runs a little bit slower. So we can solve this question by graphing an equation for each of the runners and see where those lines meet. So the first thing we need to do is write an equation for each of them. The variables need to be defined the same for both equations because we're going to put them on the same graph. So we need an x and a y. Because this is a situation where we have time and distance, we should make time the x value, and in this case that's seconds, because we're looking at meters per second, and y is going to be number of meters. So Anna's equation is fairly simple. She runs at 4 meters a second. She starts at 0 seconds and 0 meters. So y equals 4x. 4 meters every second times the number of seconds gives us the total number of meters. Now, Ray is running at 3.5 meters per second, so the slope of her line is going to be 3.5. She covers 3.5 meters every second, but we have to factor in the fact that she has a 50-meter head start. So when time is 0, she will already be at the 50-meter mark. So we have to add that 50 meters, our y-intercept, to show that when the race starts, she already has a 50-meter distance from the starting line. So in general, what this is going to look like is we'll have Ray with a head start, moving at 3.5 meters a second, and we'll have Anna starting here at the start line, but she will go a little bit faster. So eventually, she will cross Ray. So this point here is when the girls are at the same distance from the start line at the same time, which would be when Anna is passing Ray. So if the race is any longer than this many meters, then we know that Anna will win because she will have passed her. So to get that exact location, we can graph these lines using Desmos. All right, so here we are in Desmos. We're going to graph our lines. So we have Anna at y equals 4x, and we have Ray at y equals 3.5x plus the 50-meter head start. I'm going to change this to be green so it's a little closer to the color we used to write the equations. Now you can see right now that I can't even see where Ray starts running, so I need to adjust the scale of my graph. And if all I do is zoom out, doesn't necessarily help me see the situation very clearly. So we can also adjust the x and the y-axis. So x-axis, we don't need any negative times. And let's try going up to 1 minute. So at 1 minute, the lines still haven't crossed. So I'm going to add another minute. Okay, so now I'm going from 0 to 120 seconds. And now I can see where the lines cross. And at this point, the time and the distance from the starting line is exactly the same. Now note that that's not how many meters Ray has run because she had the head start, but we're looking at the distance from the starting line, which would be when Anna passes her. So that's at x equals 100, y equals 400. All right, so we have our solution. 100 seconds, 400 meters would be the part where Anna passes Ray. So if she wants to lose the race, it would be less than 400 meters. If the race is going to be a tie, it would have to be exactly 400 meters long. And if Anna wants to win, she would need to propose that the race be longer than 400 meters so that she would be ahead of Ray. Let's look at what would happen if Anna gave Ray a time head start instead. So what if she let her run for 10 seconds before she started chasing her? So we still need two equations. We're still going to let x be time and y be distance. So let's think about what a sketch of this graph might look like. So now we have Ray who's going to start at the beginning of the race, and she's going to run at 3.5 meters a second. So in this case, her line is going to be the one with the simple equation. Time starts, she's at the starting line, she runs 3.5 meters a second. Anna, however, waits a little bit, and she lets Ray run for 10 seconds before she starts running. So she doesn't start until later on, when time is at 10 seconds, and then she runs slightly faster than Ray, and then eventually she will pass her. So the question is, how can we represent this with an equation? So if Anna were starting here at the time when x equals 0, then her equation would just be y equals 4x. But she doesn't get to start running until 10 seconds into the race. So let's say the race has been going on for 12 seconds, so she's only been running for 2 seconds of the 12. If we're up to 20 seconds, Anna's only been running for 10 of those 20 seconds. So what we have to do is we have to take that x value and subtract 10 to get to how long Anna has actually been running out of the time that the race has been going. So her equation would be y equals 4, and then in parentheses, x minus 10. Now I could distribute that and get y equals 4x minus 40, and I could graph either version. All right, so now I have my two new equations. I've got Anna at 4 times x minus 10, and I've got Ray at y equals 3.5x. So now we can see, here we have in the fact that Anna doesn't start running until 10 seconds in, and we can see that the point of intersection of the line is now 80 to 80. So it takes Anna 80 seconds to catch Ray, and that would happen at 280 meters. So if she gave Ray a head start, that means the race would only have to be more than 280 meters for her to be able to catch her. So she would catch her faster with a 10-second head start than she would by giving her a 50-meter head start. Okay, so you have two things happening here. You have money that you're spending, and you have money that you're earning. So the costs that you're going to incur starting this business are $1,500 for the equipment. So that's just a one-time cost. Plus, you have to buy each t-shirt in the first place before you can put the design on it. So we need to write an equation to represent how much money you are spending to fund this business. So let's say we want X to be the number of shirts, and we want Y to be the dollars, the amount of money. And that makes sense because the money that you spend is going to depend on how many shirts you purchase. So I have to pay $1,500 no matter what, plus $3 per shirt. That's my total cost. So that's a pretty classic two-step equation right there. Base cost plus 3 per shirt. But the other thing happening here is that you're making income. So you have money coming in. So what do we know about our income from this t-shirt company? Well, it says that we will eventually sell each shirt for $20. So it's $20 per shirt. So my equation for income is going to be money equals $20 per shirt that I sell. So let's think about what's happening here. We have $1,500 that we have to spend initially, but then after that, it's only $3 per shirt. So that's going to be a pretty low slope. And then on the other hand, we're going to have a line for income. That doesn't have a y-intercept. It's going to start at 0, 0, but the slope is going to be steeper because I'm making $20 per shirt. So eventually what's going to happen is that steeper slope, the $20 per shirt, is going to overtake the line for cost. That is the break-even point. That is the point we're looking for, because after that point, the amount of money that's coming in is going to be greater than the amount of money going out. And the difference between those two lines is how we would calculate our profit, because that would be the difference between the money I've spent and the money that I am making. So let's go to Desmos and graph this and get that specific point. All right, so here we are in Desmos. I've typed in my equations, green for income, red for cost. Let us adjust our graph so we can see. I'm not going to have any negative t-shirts or negative money. Let's see what happens up to maybe 200 t-shirts. And if I'm going to have an x value of 200, my y value needs to be at least 20 times 200 or 4,000. Okay, there we go. So I can see the point of intersection. And if I click on it, Desmos will help me find it. And it is 88.235 t-shirts and $1,764.71. Now, obviously, we need to interpret this. The break-even point is a partial t-shirt. So in reality, I would need to sell 89 t-shirts to break even, meaning after that point, the amount of money coming in would be more than the amount of money going out. And we can also use the graph to find some information about profit. So for example, let's say here at 100 t-shirts, I would have made $2,000 and I would have spent $1,800. So that means that at that point of selling 100 t-shirts, my profit would be $200. So that's why a graph is useful. Beyond just answering the question of the break-even point, it allows us to see a little bit more information about the scenario.